Hi guys, nice to see you, each one of you here. And I think this will help you in getting into the rope because many of you are absent or many people are availing leave. So I just wanted to help you people. So I think this will help you maybe. So this is your first unit. Okay. So this is fully regarding conductors. Okay. So when you say conductors, the first thing what comes to your mind is just metals. It doesn't mean that metals are the only conductors available. There are many kinds of conductors available. For example, other than metals, you have something known as polymer. Of course, in polymers, it can be conducting polymers or semiconducting polymers. What is that one? Insulating polymers. But now we are just considering these metals as conductors. So to start with, why do we have metals as conductors? As you know, this metals has numerous applications. I think you all know what are all the applications. For example, these metals are generally used in the field of industry, or it is used in defense, or it has medical applications, and it goes on. So why metals are having these applications? That is what you have to reason it out. When you peep through, these metals are having interesting physical properties. What do you mean by these interesting physical properties? What are all the things? So it has many properties like resistivity, of course electrical or thermal both. When there is electrical resistivity, there will be thermal resistivity. So generally both will be alike, and it can be even resistance to corrosion, or it can be stiffness or hardness, or this list also moves on. So there are some interesting physical properties, and these physical properties are the reason for this metal to be useful in these applications. So why metals are having these physical properties? To begin our discussion, this is going to be the starting point for all our discussions. So we have to say why metals are having these special properties. Understood? So now, to reason out all these things, we are going to discuss certain things. Okay? So I'm repeating. So these metals are having numerous applications in all these fields. Why? Because of these important physical properties. These special physical properties are the reason for which why metals are used in different fields. Now we have to reason out why there are these physical properties. Okay, so that is going to be our beginning point. The thing was reasoned out in 1900. There were two people. One man is named Drude, and he proposed a theory to reason out why metals are having these properties, and that is known as Drude theory, right? And there were some corrections. Then came a man known as Lorentz. Together, all this one is known as classical free electron theory. Okay, classical free electron theory. And this is what first thing we are going to see now. This was first proposed by this Drude, then it was given as minor modification by this Lorentz. But even with all these things, there are many discrepancies. Okay, even with all these things, it has several discrepancies. And later we have to go for correction, and then came this quantum theory. Okay, so quantum free electron theory. So slowly we can get into our syllabus. Okay, so our first thing is going to be this Drude theory. Okay. So to begin with, we all know that in any atom there is a center nucleus, and this nucleus will be surrounded by the shells known as energy levels. You know, this nucleus is going to contain protons and neutrons, isn't it? And all this shell will be surrounded by electrons, or maybe this symbol denotes electron. Okay, E minus, whenever I write it is electrons. Okay, P for proton and N for neutron. For example, consider Na atom. Okay, you know Na, right? Sodium. This sodium has atomic number. You know what is the atomic number of sodium? It is 11. So how the shells will be filled? I am going to write its atomic configuration. Okay, so 1s2, 2s2, 2p6, 3s1. Okay, and if I am writing that one in this structure, my nucleus, it will be surrounded by 2 electrons first, isn't it? Then all the guys are present, and there is one outermost shell. It will have only 1 electron. This is going to be my 3s1 electron. This has 6, 2, 3, 4, 5, 6. Okay, and this has 2. This is just a pictorial representation. This thing cannot be like this. Okay, so this outer shell contains only 1 electron, that is 3s1 electron. Now this 3s1 electron is known as free electron. Okay, it has some other name. You can also call it as conduction electron. Okay, you can even say it as valence electron. So these are all the names. Okay, now you have to know what is a free electron. Hope you understand this one. The electron that is present in the outermost orbit is known as free electron, right? And these electrons, there are 10 electrons, right? These 10 electrons are known as bound electrons. Okay, so these things are known as bound electron. They will not take part in conduction. They are closely bound with this nucleus. There will be attraction with the nucleus, so they cannot come out. But whereas the electron in the outermost shell will experience small or least Coulomb attraction from this nucleus. So these things or these guys are generally free to move everywhere in the metal. So that is why it is known as free electron. They are free for conduction. Okay, so I am repeating, those electrons that are present on the outermost orbit is known as free electron, and you can also call it as conduction electron. Sometimes it is also called as valence electron. Only these valence electron will support conduction. So these are known as free electrons. Okay, I think you can understand what is meant by free electron. In this case, when you are talking about this free electron, you may ask, it is not only this single atom or single electron that is present in the metal. There will be many free electrons present. But the thing is, these free electrons are not generally repelled by each other. Of course they are repelled, but we are negotiating all those things. So what are all your approximations? There are certain approximations that you have to be lenient, or you have to know. The first one is this inter electron or Coulomb force is neglected. Okay, what does it mean? You say that the electrons are not interacting. Okay, so this is what your approximations. So with these approximations, we also propose certain things which forms the basis for your Drude theory. So this is the general discussion. Now we are getting more into your Drude theory. So as discussed, that is what you generally say. There is a nucleus surrounded by electrons. Now Drude's model says like this. First thing being, there is a positive ion core. So this positive ion core is surrounded by electron gas. Okay, so this is your electron gas. There will be a positive ion core surrounded by electron gas. That is what Drude says. Now you can assume like a thing, maybe I have a container containing ideal gas. Okay, what will happen to the gas? All the molecules will move in all the direction. It will exhibit random motion. Of course, it will have any velocity. The metal block will have free electrons. These free electrons will also exhibit random motion. Okay. Both are exhibiting random motion in all possible velocities. Now this ideal gas obeys all classical laws. This metal free electrons will also obey all classical laws. That is your basic consideration. Okay. So both things are synonymous. Now both guys obey kinetic theory of gases. Now as these are moving in all possible direction with all possible velocity, we are going to define something known as thermal velocity. It is the average velocity of the electrons. Okay, that is known as thermal velocity. So when these electrons are moving in random motion, they have the velocity given by this thermal velocity, that is an average value. Now while moving, they can collide with each other. Then we are defining something known as mean free path. It is given by lambda and this is denoted by v. Okay, this lambda is the mean free path, that is the distance between two successive collisions. An electron moves this way and here this is one E1. Okay, and electron is maybe E2. This guy comes in this way. They are colliding here. So now this is your mean free path. Distance here, of course, here there is some other electron E3, it already has struck here. So this distance between two collisions is known as mean free path, or the time or the distance traveled by electron without colliding with any other electron is this mean free path lambda. Understood? The distance traveled between successive collisions is known as mean free path, right? And the time taken for this one, let us denote that one by this symbol T. Okay, this T is always lambda by V, where V is this thermal velocity. Okay, so this is the basis for the discussion or the assumptions in Drude theory. So with this we have to derive expression for thermal conductivity and electrical conductivity. So hope you find this useful. Maybe this is going to be this part 1. The later things will be discussed as expression for electrical conductivity followed by expression for thermal conductivity, and that will lead you to this Wiedemann-Franz law, and that will lead you to your Lorentz number, and after that we can see what is this discrepancy in this one, this classical free electron theory, and we can get into quantum theory, which will take you to density of states followed by your carrier concentration, and that will be the end of your first unit. So see you in next session. Bye.